Okay, so in this chapter, we're going to start thinking more about waves, which can be repetitive motions of an object itself, like a standing wave on a string, or it can be propagating disturbances in a fluid medium, like the sound waves that we hear, or waves on the surface of the ocean. Right? So in this chapter, we'll start things off by revisiting the simple harmonic oscillators that we talked about a little bit in the chapter where we looked at mechanical objects like springs. And in section 10.1, we'll think about using simple oscillators as a way to help us keep track of time. That will give us the language that we need to think about sound waves, which are disturbances in the air around us, and the kind of musical instruments that can produce them. That's what we'll see in section 10.2. And then 10.3, we'll close things out by looking at ocean waves and the tides and that kind of thing. So back in that section on mechanical objects, we learned about motions governed by Hooke's law, right? So let me just remind you, Hooke's law, which said that the restoring force that an object experienced, if you had, say, a spring, was given by some constant, the stiffness of the spring, multiplied by the distortion, how far away you had pulled that object from equilibrium. So for instance, if you have like a spring attached to a wall, and on the end of it you have some mass, this would be the equilibrium position of the spring, where the object wants to kind of just sit when you don't apply any forces. And if you stretch this spring so that now the object is sitting out here and you have a stretched spring, you will have distorted the spring away from its equilibrium position, and the object will feel a restoring force that wants to bring it back this way. And similarly, if you compress the spring so that the object is sitting over here, it experiences a restoring force pointing back to its equilibrium position. Okay. So we talked about how this whole process, we could also think about trading kind of elastic potential energy from stored in the spring to kinetic energy of the moving object. So if we pulled this spring, if we stretched it, we were storing a lot of elastic potential energy in the spring. If we let go, the mass would start accelerating. As the elastic potential energy got converted into kinetic energy, the mass would accelerate. It would be going fastest when it got back to its equilibrium position, and then it would kind of start decelerating as the spring compressed. It would briefly pause, and then it would turn around and repeat this cycle over and over again. Right? One of the things that we didn't talk about was how long does it take to go through this process? How long does it take to complete one of these cycles? To complete such a cycle? So for instance, if I plot in a graph the position of the mass as a function of time, so if I call this the equilibrium position, then if I stretch it, if I stretch the spring, maybe that's like starting it over here, what's going to happen when I let go is that this position is going to kind of oscillate back in time. And my hands are a little bit cold right now, so it's hard for me to draw neatly. But this oscillator will kind of go back and forth between one position and the other, and the other, and the other, going fastest here, and here, and here, and here, going back and forth. And something we didn't ask, or we didn't answer at the time, was how long does it take to go from where it started back to its original position? Or how long does it take to go from here back through one full cycle? Right? Let's try to answer that question, right? So what possible things could the answer depend on? What could this depend on? Well, on the one hand, of course, it could depend on the object's mass, right? When we stretch the spring is going to be applying a force to this mass, and the mass of the object tells us how much the object will accelerate in response to any given force. Right? So the mass of the object, I think that makes sense, that might matter. Also the stiffness of the spring. Stiffness of spring. Okay, the mass tells us how much the object will accelerate in response to a given force, and the stiffness of the spring tells us what the magnitude of that force is going to be at any given amount of distortion. Right? Another thing that, at least in principle, could depend on is the amplitude of motion. The amplitude of motion. That is to say, how far back did we pull the mass in the first place? Where did we get this thing started? And the amplitude of a wave-like pattern like this is the kind of magnitude of the total greatest separation between 2 points on the wave, right? So the kind of distance from the height of this peak relative to this trough, for instance. So in principle, it could depend on all of these things, and that's kind of everything that we've set up in this problem, right? We have a mass, we have a spring, and we've stretched the mass to some new position. Those are the 3 things that this kind of length of the cycle could, in principle, depend on. Okay. One of the remarkable things about simple harmonic oscillators, though, that is, when Hooke's law is obeyed and the force is exactly proportional to the displacement, is that it turns out the amplitude of motion does not matter. And so if I start the spring by stretching it not as much, it's going to kind of have the same overall period of motion. It's going to have the same overall period of motion. This is, again, a consequence of Hooke's law, and when you have a force that's proportional to the current displacement, you have this kind of property, right? So if you have an oscillator that has a larger amplitude, it'll certainly travel a greater total distance each time it goes through, one cycle, but they are experiencing larger maximum restoring forces, they get up to greater maximum speeds, and so they cover that greater distance in actually exactly the same amount of time as an oscillator with the same spring constant that was stretched to a different amount. So what this means is that the period of oscillation, and this is what we'll use to refer to like this length of time. How long does it take to go from where I initially stretched the spring to all the way back to where it started, or from here, to compression back to extension. So it's the period of the oscillation. That means that the period of oscillation depends, for these simple harmonic oscillators, depends only on mass and spring constant. And actually, that means that dimensional analysis can already tell us what the basic dependence of the period of oscillation is on these new quantities. So if I call the period of oscillation capital T, then the dimensions of the period is just, it's an amount of time. Of course, mass has dimensions of mass. And what about the dimensions of the spring constant? Well, if we go back to Hooke's law, we know forces, those have, units of kilograms, meters per second squared, or dimensions of masses times lengths divided by 2 powers of time. So if that's the dimensions of force, that means that the dimensions of the spring constant must be dimensions of mass divided by 2 powers of dimensions of time. So if the oscillation period is some function of m and k, how can I combine these types of units in order to get something that has the right overall dimensions? And the answer is that the period of oscillation must depend on the square root of the ratio between these two things, the square root of the mass of the object divided by the spring constant, right? And you can see that if I take the dimensions of mass and I divide it by the dimensions of the spring constant, I'll get dimensions of time squared. Taking the square root gives me dimensions of time. And then if you do the actual math involved, you find what this precise constant of proportionality is that makes this an equation. And it turns out to be the number 2 times pi. Okay? So the period of one of these simple harmonic oscillators is 2 pi times the square root of the mass divided by the spring constant. We could also express that by talking about the frequency. And the frequency is, I'll use little f to denote the frequency, is just 1 divided by the period of any kind of oscillation. Okay? And so looking at this expression, I can see that I could write the frequency, how many cycles happen per unit time, as 1 over t, and that's going to be equal to 1 divided by 2 pi, multiplied by the square root of, and now it's k divided by m. Okay. The dimensions of frequency are 1 over time, and the SI units of frequency, are 1 inverse second, so 1 per second, which is also defined as the hertz, abbreviated Hz. Okay. So if you have an oscillator that takes 4 seconds to get back to where it started, that means it has a period of 4 seconds and a frequency of 1/4 of a hertz. Or similarly, if you have, say, an oboe in an orchestra playing an A note, sometimes called A4 or middle A, which has a frequency of 440 hertz. We'll see what this means when we talk about sound waves, to have a sound at a certain frequency. Something about the air, okay, is going through a cycle that happens 440 times per second, or, so that's the frequency, or it has a period of 1 divided by 440 seconds, which is about 0.0023 seconds. Okay. So something about a vibration in the air takes a few milliseconds when an oboe is playing middle A, and something about it is oscillating with a frequency of 440 oscillations per second. Okay. What we've just learned is that simple harmonic oscillators, this is section 10.1.2, where we talk about resonance and natural frequency. Simple harmonic oscillators have what we might call a natural frequency, some particular frequency associated with their motion about a stable configuration. Right? So if I have this mass on a spring, it doesn't matter if I pull it a little bit or a little bit more. The natural frequency of this oscillator is just determined by, this particular combination of the stiffness of the spring and the mass of the object. Okay? All sorts of things, though, have natural frequencies. When you bump, say, into a rocking chair, it'll rock back and forth at some particular frequency, which is determined by how it's shaped and how much it weighs. If you have, the strings on an instrument, after you pluck them, the string will vibrate back and forth at some particular natural frequency, right? And in most systems, friction cannot be ignored. And so as the object is oscillating, those oscillations eventually decay away, they kind of die out, right? Like when you bump into a rocking chair, it rocks back and forth, but it rocks back and forth a little bit less until eventually it comes back to rest. So to keep oscillations going, what you can do is make use of resonances. And a resonance, or resonant driving, is when the amplitude of an oscillation can be either maintained against friction or actually increased by periodically applying a force at a particular frequency which is close to the natural frequency of that oscillation. For example, and this is something that if you've ever played on a swing set, right? So on a swing, you have well, let's just draw a swing, and we've got a person sitting here. At first, let's say they're just sitting there, but if you stand over here and give this person a little forward push, every time that they're moving forward, you'll gradually make them go higher and higher, right? And the idea here is that if you just start this person off, so let me draw this a little bit more simply. If you start this person off, and I'll just draw the swing as if it's some pendulum, there'll be a natural frequency of the oscillations of this, and those will decay away because of the friction in this pivot and because of drag. But just like the simple harmonic oscillator, there's a natural frequency that doesn't depend on the amplitude of this motion. And so if you give this person on a swing a push timed once per cycle, then you will achieve what's called resonant driving. You're applying a periodic force at a frequency that's basically the same as the natural frequency of that oscillation of the swing, and that will make the swing, oscillate more and more. Great. So you can either reinforce the natural oscillatory motion to make the oscillation amplitudes bigger, or you can just have a magnitude that's big enough to just compensate for the energy loss due to friction or drag or whatever. But it's important that you time your pushes to the natural frequency of the oscillation. If you just pushed your friend at random times, then you would not reinforce this cycle, and it wouldn't be very fun. This idea of applying forces with a frequency that matches or nearly matches a system's natural frequency is a very general one that lets us sustain all kinds of mechanical oscillations, like either these springs or swings in the kind of examples we just discussed. It's also how, for instance, singing at a wine glass can actually make the glass break. A wine glass, just like basically every other nice crystalline solid object, has a natural frequency that it wants to vibrate at. And that's why when you ding a wine glass, it rings out with a certain note. Well, if you sing, creating vibrations in the air at that same frequency, the wine glass's natural frequency, you'll amplify the magnitude of those tiny oscillations in the wine glass until eventually the glass is physically moving and vibrating so much that it breaks. And in the lecture notes, I've included a link to a YouTube video which demonstrates someone doing exactly that. Okay. So this is this idea of resonances and natural frequencies. So periodic forces applied close to an object's or a system's natural frequency can reinforce or maintain the oscillations. Another way of saying this is that when an object is oscillating back and forth, it has a certain amount of energy in that oscillation. So in this simple harmonic oscillator where we're ignoring friction, there's a total energy associated with the elastic potential energy and with the kinetic energy of the mass. And so there's a certain total energy in this oscillating system. And if you periodically apply forces that are close to a system's natural frequency, you can add energy to that system. And that's what we mean by reinforcing the oscillations, making them bigger, or maintaining them. So adding energy to this oscillation, even as friction or drag or other things take energy away from it. Okay. This idea of resonance and natural frequencies and so on and so forth also lets us build clocks. Right? So timekeeping devices have been around for an extremely long time, based on tracking how long periodic occurrences happen in the natural world. So for instance, sundials. We've built our time system around the idea that the length of one day-night cycle is very close to 24 hours, which we then break up into hours and minutes and seconds and so on. And by watching, the length of the daytime at the equator is 24 hours. And so the length of the daytime at the equator is 24 hours. And so by watching, say, the motion of a shadow that a vertical pole is casting during the day, you can know what fraction of the day has elapsed since sunrise. That's not particularly helpful on a cloudy day or if it's nighttime, but it's something, right? It lets you get a sense of how much time has elapsed since some event. Right? Shorter periods of time could be measured by tracking things like hourglasses or water clocks. So for instance, you could fill an hourglass with a certain amount of sand and then, wait and ask how long does it take all of that sand to run out from the top compartment to the bottom compartment. Or you could do a similar thing by filling a bucket that has a small hole in it with a bunch of water and asking how long does it take for all of the water to empty out of the bucket, right? Actually, water clocks were basically the state of the art in clock technology until pendulum-based clocks came around. And pendulum-based clocks are really just making use of this same picture of a simple harmonic oscillator. So let me draw a pendulum, which is a heavy mass suspended by a string or rod, something which weighs an insignificant amount compared to the mass of this object itself. And when this pendulum is just at rest, what forces are acting on it? Well, there's just, the object's own weight, m times g, pulling the thing straight down. But it's not in motion, and so there's some tension in this string. Well, if we, tilt the pendulum so that it's at some angle relative to where it used to be, we still have, so there's a force of some tension. There's still some tension pointing this way along the string. And there's still the object's own weight, which is pointing straight down, m times g. But now you'll notice that the tension force and the force due to the object's own weight are not able to balance each other because the tension does not point in the right direction. So there's a component of the object's weight, just like if you put an object on a ramp, that points in the direction of the equilibrium, of the pendulum's equilibrium or rest position. And similarly, so the pendulum will start accelerating this way. It'll reach a maximum velocity when it's right underneath the pivot point. It's going to slow down as it swings back up here until it gets to the same angle. And, on this side of the equilibrium position, gravity is still pointing straight down, tension in the string is now pointing this way, and there's a net restoring force pointing this way, which will cause the pendulum to swing back and forth, right? So it turns out as long as you keep the amplitude of the oscillations reasonably small, this whole system is exactly like a simple harmonic oscillator, down to the fact that the magnitude of the restoring force is also basically proportional to the displacement of the pendulum away from its equilibrium position. So we can think about the period of a pendulum. How long does it take to swing from, over here, over to here, and then back to where it started? Just like in the case of a simple harmonic oscillator, it's going to be a competition. There's going to be a competition between the mass of the object itself and the thing that's supplying restoring forces to this object, right? So it's still a competition between the mass and the restoring force. But here, the restoring force is due to gravity. And so the magnitude of the restoring force also depends on the mass of the pendulum itself, since the restoring force is going to be mg, in this case, times the sine of theta. Okay. What that means is that actually for these idealized pendulums, where the mass of the pendulum is much larger than the mass of the string suspending the pendulum, the period of oscillation doesn't even depend on how heavy the pendulum itself is. It depends only on the length of the pendulum and the acceleration due to gravity. So you end up with an expression that says the period of a pendulum is just 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity. So short pendulums swing back and forth more frequently than longer pendulums. Or swings, which are basically just long pendulums, have a period of oscillation that just depends essentially on how long it is from the seat to the pivot. Okay. Now, one challenge is that, pendulums are really, as clocks, designed to operate for very long periods of time. And so there's lots of opportunities for friction about the pivot point or drag from this, I think it's called the pendulum bob, swinging back and forth through the air to slowly take energy away from the pendulum, making the oscillation amplitudes very slightly less and less over time. And so when you're designing an actual pendulum clock, what you need to do is have, a pendulum bob here. This pendulum rod is typically connected to like a little set of teeth that kind of rotate back and forth, which themselves move a gear, and that gear is connected to the minute hands and second hands and hour hands of the clock. So this gear gets rotated by these teeth arms connected to the top of the pendulum rod. And in order to keep this whole contraption going, you'll add a hanging weight, which has its own pull due to gravity, which very slowly, at the resonant frequency of the pendulum itself, adds tiny amounts of energy back into the pendulum's oscillation to compensate for drag and friction and all these things. Great. Great. Pendulum clocks are great, and they were actually the standard of timekeeping from about the mid-1600s to the early 1900s. But pendulum clocks have some problems that are difficult to get around. One, you can only use them on perfectly flat and level surfaces, and that means if you wanted to keep time on a boat, you had a very hard time using a pendulum clock. And in the lecture notes, I make some comments about how keeping time on the open ocean is intimately related to knowing where on the Earth's surface you are, how far east and west you've traveled. You can figure that out if you just have a really good clock. Modern timekeeping devices use basically these same principles, relying on fixed periods of simple oscillating devices making use of the natural frequencies that different things will vibrate with. Mechanical watches, for instance, make use of a tiny oscillating wheel called a balance wheel, which is connected to a spring which exerts torques on the wheel. So it's a torsional spring that makes the wheel kind of rotate back and forth like this, rather than a linear spring, which would make it go back and forth like so. And the nice thing about balance wheels and torsional springs is that gravity doesn't exert a torque on the balance ring, which means you don't need to have a balance wheel driven watch perfectly level on your arm at all moments. More modern electronic watches make use of oscillations, not of mechanical devices, but actually extremely small crystals made out of quartz. So quartz, this is just a fun aside, I suppose. Quartz crystals have what's known as piezoelectric properties. And what this means is that if you apply an electric charge or an electric field to a tiny quartz crystal, that crystal will feel like you're pushing on it or pulling on it, depending on how you apply the field. And similarly, if the crystal gets compressed or expanded, it will generate tiny electrical fields. So quartz crystals, they have this piezoelectric property, and they also have their own natural frequency of oscillation, right? I want to emphasize, you can, great, I've got a soup ladle over here. Basically any object, especially nice solid objects composed of mostly the same material, will have like a frequency that they want to resonate at, and you can hear that just by hitting the soup spoon sufficiently hard on your hand so that you get it to resonate a little bit, right? So this soup ladle has a natural resonant frequency. Crystals have some natural resonant frequency. For these small crystals, it's really very fast. But by having this piezoelectric property, it's kind of nice. It means that you can kind of create electronics that both measure the tiny vibrations of the crystal, because the tiny vibrations of the crystal will generate their own tiny electrical fields. And you can also use separate electrical fields to, keep the crystal vibrating so that it doesn't slowly lose energy over time. Okay, great. So that's kind of our introduction to kind of simple mechanical oscillating systems. And we'll see a lot more about how some of these mechanical waves behave in the next sections, again, where we talk about musical instruments and ocean waves.